Psych, at the exact center of our galaxy sits something 4 million times heavier than our sun, packed into a space smaller than the orbit of Venus. We've given it a name. We've photographed its shadow. We've won a Nobel Prize for finding it, and we still haven't proven what it actually is. Not because nobody's tried. For over half a century, some of the sharpest minds in physics have thrown everything they have at this single object. Starlight, radio waves, gravitational math, an image assembled from a telescope the size of the entire planet. And every single test keeps landing on the same maddening conclusion. It looks exactly like a black hole should look. It behaves exactly like a black hole should behave. But looking like something and being that something are two very different claims. And in early 2026, a team of astrophysicists in Argentina published a result that should make you uncomfortable. An entirely different kind of object, made of matter we've never directly detected, that could produce the exact same evidence. Orbit for orbit, shadow for shadow, as the black hole we assumed we'd already found. This is the story of Sagittarius A star. Not a monster we're trying to measure. A mystery we've been mistaking for a settled fact. Before we begin, if you're curious about the universe and the incredible stories hidden within it, consider liking the video and subscribing. Every bit of support helps us bring more fascinating discoveries to curious minds around the world. Now, let's begin. Every mystery needs a first clue, and this one starts with a young radio engineer who wasn't even looking for it. The year is 1933. Karl Jansky, working for Bell Labs, is trying to track down the source of static interfering with transatlantic radio calls. Nothing glamorous, a technical nuisance, the kind of problem an engineer gets assigned because someone has to. But as Jansky sweeps his antenna across the sky, he finds a signal that doesn't behave like the others, a hiss that rises and falls with sidereal time, tracking the stars rather than the sun. He traces it to a single patch of sky, toward the constellation Sagittarius, toward the center of our own galaxy. Nobody had a framework for what that meant. Black holes at the time weren't taken seriously as real objects. They were mathematical curiosities buried in Einstein's equations, the kind of thing physicists debated but didn't expect to actually find. So Jansky's signal sat there, cataloged as Sagittarius A, an interesting radio source with no clear explanation, for 4 decades. Other researchers picked up pieces of the same puzzle without realizing what they'd stumbled onto. In Australia, radio astronomers working at facilities near Sydney identified a distinct, unusually bright source in the same patch of sky, describing it only as a probable galactic center candidate. It was treated as an interesting landmark, not a monster in disguise. The same quiet, patient misunderstanding that would echo years later and 18 billion light-years away in the story of TON 618. Two very different objects, discovered decades apart, both sitting in plain sight under names too modest for what they actually were. Then, in February 1974, astronomers Bruce Ballack and Robert Brown pointed a radio interferometer at that same patch of sky and found something buried inside the larger source. A small, unusually bright compact point. Brown later gave it a name, Sagittarius A star. The asterisk wasn't decoration. In physics, an asterisk denotes an excited state, and Brown thought this object earned one. But naming something isn't the same as understanding it, and for another 20 years, Sagittarius A star remained exactly that. A name attached to a bright dot, with theories piling up around it, and none of them confirmed. Could it be a dense star cluster? A supernova remnant? Something else entirely? The debate simmered through the 1980s, unresolved, because there was no way yet to measure what was actually happening at that location. The breakthrough came from patience, not new instruments. Starting in the 1990s, 2 teams, one led by Reinhard Genzel in Germany, another by Andrea Ghez in the United States, began tracking individual stars orbiting that bright, dark patch of sky. Not one glimpse, years of glimpses, plotted year after year, watching orbits slowly trace themselves out like a hand drawing an ellipse one dot at a time. What they found should have ended the story right there. A star called S2 was completing an entire orbit around Sagittarius A star in under 16 years. For comparison, our own sun takes over 200 million years to circle the galaxy once. S2 was moving at speeds up to 2.5% the speed of light at its closest approach. And by tracking exactly how S2 curved through space, both teams calculated the mass required to bend its path that way. Roughly 4.3 million suns, crammed into a region you could fit inside the orbit of Mercury. There is no known star massive enough to collapse into something like that. There is no known cluster of smaller objects dense enough to hide in that smallest space without colliding into each other constantly. By process of elimination, both teams reached the same verdict, and in 2020, Genzel and Ghez shared the Nobel Prize in Physics for it, split 3 ways, with the final share going to Roger Penrose for proving mathematically that black holes are an unavoidable consequence of general relativity. It's worth sitting with just how strange that orbital data really is. S2 doesn't drift lazily around Sagittarius A star the way Earth drifts around the Sun. At its closest approach, it swings within about 120 astronomical units of that dark central point, roughly the distance from the Sun out past Neptune. And does it at 2.55% the speed of light, close enough that general relativity itself predicts a measurable gravitational redshift in its light. In 2018, astronomers caught that redshift directly, matching Einstein's prediction with a precision better than 10%. Whatever sits at that focus point isn't just massive, it's massive and compact enough to bend both space and time in ways we can now measure star by star, orbit by orbit. Case closed. Except, and this is the detail that gets glossed over almost every time this story gets told, read the actual wording of that Nobel citation. It doesn't say, for the discovery of a black hole. It says, for the discovery of a supermassive compact object at the center of our galaxy. The Nobel Committee, writing the most prestigious scientific endorsement in the world, chose its words with obvious, deliberate care. They confirmed something is there. They stopped just short of confirming what it is. Here's the problem hiding underneath 50 years of confirmation. A black hole, by definition, cannot be observed directly. It emits no light. Anything that falls past its event horizon disappears from our instruments completely. So, every single piece of evidence we have for Sagittarius A star being a black hole is indirect, inferred from how things around it move, never from the thing itself. That distinction matters more than it sounds like it should, because indirect evidence can, in principle, be explained by more than one cause. Stars orbiting a hidden mass tell you there's mass there. They don't automatically tell you that mass is a singularity wrapped in an event horizon, rather than something else entirely, provided that something else bends gravity in a similar enough way. And that's exactly the gap several competing models have tried to slide into. Boson star models propose Sagittarius. A star is built from an exotic class of particle rather than collapsed matter. Gravastar models propose a shell of ultra-dense energy wrapped around a dark matter interior. And then there's the model that's recently forced its way back into serious discussion, a compact core made entirely of dark matter. The idea itself isn't new. It traces back to a 1969 proposal by physicists Ruffini and Bonazzola, describing how a specific kind of dark matter particle, a fermion, could theoretically clump together into something dense enough to mimic a supermassive black hole. For decades, that idea sat quietly in the background of the literature, unfashionable, unconfirmed, mostly ignored while the black hole explanation kept accumulating supporting evidence. Then, In February 2026, a team led by Valentina Crespi at the Institute of Astrophysics in La Plata, Argentina, did something nobody had rigorously done before. They took that old fermionic dark matter model and tested it directly against the same orbital data used to justify the black hole conclusion. The path of S2 plus 5 mysterious objects called G objects that behave like stars but visibly stretch and distort like gas clouds as they pass close to the galactic center. Those G objects deserve a moment of their own because they're strange enough to be a mystery all on their own. First identified in the early 2000s, they orbit Sagittarius A star the way stars do, on regular, predictable paths. But their shape isn't stable the way a star's should be. As they swing close to the black hole candidate, they visibly stretch and distort, behaving less like a solid stellar body and more like a loosely bound cloud of gas and dust wrapped around something denser inside. Nobody fully agrees on what they are. Any model claiming to explain Sagittarius A star has to also explain why these 5 objects behave the way they do. And that's exactly the bar Crespi's team set for themselves. The result, published in the monthly notices of the Royal Astronomical Society, is the reason this story needs telling again. A dense core of fermionic dark matter reproduced those same orbits to within less than 1% of the precision achieved by the black hole model. Read that again. 2 completely different physical objects. One a singularity wrapped in an inescapable boundary. The other a stable, dense sphere of exotic particles with no boundary at all. Produce gravitational effects on nearby stars that are, with our current instruments, functionally indistinguishable. We haven't been staring at confirmed proof for the past 50 years. We've been staring at the best supported guess. Helps to understand why dark matter was ever a serious candidate for this role in the first place. The idea goes back to the 1930s, when physicist Fritz Zwicky noticed that galaxies inside the Coma cluster were moving far too fast to stay gravitationally bound by the visible matter alone, at speeds that should have flung the cluster apart entirely. Something invisible had to be supplying the missing gravity. Decades later, the same pattern showed up again in individual galaxy rotation. Stars in the outer regions orbiting faster than visible mass could explain. Today, dark matter is thought to make up roughly 85% of all matter in the universe, wrapped around galaxies like ours in enormous diffuse halos. And yet, despite permeating essentially everything we can see, it has never been directly detected. We know it's there purely from its gravitational fingerprints, which is exactly the same category of evidence we have for Sagittarius A star. So why would dark matter, of all things, behave like this? The answer sits inside a rule you've actually experienced yourself, even if you've never thought about it in these terms. Fermions, the category of particle. This theory proposes dark matter belongs to obey something called the Pauli exclusion principle. 2 identical fermions cannot occupy the exact same quantum state at the exact same time. It's the same rule that keeps electrons from collapsing into each other inside atoms, and it's the reason you can't walk through a solid wall. Matter pushes back against being squeezed past a certain point. If dark matter is made of fermions, that same resistance applies. Pack enough dark fermions into a small enough space, and rather than continuing to collapse forever into a singularity the way ordinary matter does inside a black hole, they hit a wall of internal pressure and simply stop. The result is an object dense enough to warp space-time like a supermassive black hole, but structurally nothing like one. No singularity, no event horizon, no true point of no return. This isn't a fringe idea invented to explain away an inconvenient result either. It was first proposed back in 1969 by physicists Ruffini and Bonazzola, decades before anyone had the instruments to test it against real orbital data. It sat quietly in the scientific literature for over 50 years, neither disproven nor confirmed, waiting for measurements precise enough to actually put it to the test. Crespi's 2026 paper is, in a sense, the first time that 50-year-old idea has finally been given a fair hearing. And there's a detail here the black hole model can't easily match. Astronomers using the European Space Agency's Gaia mission have been mapping the motion of over 1 billion stars across the Milky Way. And in 2022, that data revealed something odd happening at the galaxy's outer edge. The rotation speed of the outer arms drops off faster than most dark matter models predict. Standard dark matter theories struggle to explain that sharp decline, but a fermionic dark matter halo, thanks to that same exclusion principle, would naturally form a sphere with a much sharper edge than other dark matter candidates, producing exactly the kind of rotational drop-off Gaia detected. Here's where the decision gets genuinely difficult, because this isn't just a story about the galactic center anymore. If Sagittarius A star really is a fermionic dark matter core, the model proposes it isn't a separate structure from the dark matter halo enveloping our entire galaxy. It's the same continuous substance, simply denser at the center and more diffuse toward the edges. One object, not two. No competing model unifies the galactic center and the galaxy-wide dark matter halo into a single structure the way this one does. Which leaves astrophysics with an uncomfortable choice. Either accept that Sagittarius A star is a black hole, the simpler and far more established conclusion, backed by 50 years of converging evidence and a Nobel Prize. Or take seriously the possibility that the exact same evidence could be explained by an object made of a particle we've never directly detected. And that this same particle might also solve one of the biggest unanswered questions in physics: what dark matter actually is. Neither option can currently be ruled out. And that's precisely why this isn't a fringe theory being humored out of politeness. It's a genuine open question sitting at the center of our own galaxy. In May 2022, the world got its answer, or thought it did. The Event Horizon Telescope, a network of radio observatories spanning the globe stitched together into a single virtual instrument, released the first image of Sagittarius A star. A glowing ring of superheated gas, bent by extreme gravity, wrapped around a dark central shadow. Producing that single image took 5 years of processing after the data was even collected, combining observations from 8 radio observatories across 6 sites around the planet, all synchronized to the same instant, all correcting for the fact that Sagittarius, a star's emission, flickers on a timescale of minutes rather than staying still like most sources astronomers are used to imaging. It remains only the second image of a black hole shadow ever produced, after the much larger, much calmer black hole at the center of galaxy M87 in 2019. It was treated almost universally as the final confirmation. A photograph of the black hole itself. Except that's not quite what the image shows. Light cannot escape a black hole, which means a black hole can never actually be photographed. What the EHT captured was glowing matter circling something, bent into a ring by whatever gravity source sits at the center, with a dark shadow cast against it. That image is consistent with a black hole. It is not exclusive to one. In a 2024 follow-up study, Arguelles and his collaborators, the same team behind the fermionic dark matter model, demonstrated that a sufficiently dense dark matter core would bend light just as strongly as a black hole's event horizon, producing a shadow surrounded by a bright ring that our current instruments cannot distinguish from the genuine article. The iconic photograph didn't settle the debate. It became evidence that both sides could claim. So picture standing, hypothetically, near enough to tell the two apart. If Sagittarius A star is a true black hole, there's a specific signature waiting to be found: a photon ring, created when light passes close enough to the event horizon that it's forced to loop around the black hole multiple times, spiraling in tighter and tighter orbits before either escaping in a faint secondary ring or vanishing forever. That effect requires an actual event horizon to trap and bend light that severely. A fermionic dark matter core has no event horizon. Light passing near it would bend, same as it does near any sufficiently massive object, but it would never get trapped in that recursive spiral. No true photon ring. If we can ever image that specific signature around Sagittarius A star, the debate ends, genuinely, not provisionally. We're not there yet. NASA's proposed Black Hole Explorer mission aims to launch a new space-based radio telescope that could link directly into the next generation of the Event Horizon Telescope, effectively building an instrument larger than Earth itself. That could take decades to become reality. In the meantime, the gravity interferometer in Chile is already tracking a subtler clue: the precise way S2's orbit slowly rotates over time. A relativistic effect called pericenter precession, whose exact direction and magnitude could quietly favor one model over the other long before any photon ring is ever photographed. And there's a second front entirely, one that has nothing to do with telescopes. If dark matter really is built from fermions, it should be detectable directly, here on Earth, without ever pointing a lens at the galactic center. Experiments like South Korea's Neon detector are hunting for the faint traces left behind when a passing dark matter particle collides with an electron. A signature so subtle, it spent decades eluding every search. Find that signal, and Sagittarius, a star's identity gets resolved from a basement laboratory, not a telescope pointed at the sky. There's one more piece of this that reaches further than our own galaxy. The James Webb Space Telescope has been finding compact, extraordinarily massive objects at the centers of galaxies so distant, we're seeing them as they existed less than 1 billion years after the Big Bang. Objects nicknamed little red dots, hundreds of millions to billions of solar masses, sitting at a point in cosmic history that leaves almost no time for a black hole to have grown that large through ordinary means. A fermionic dark matter core doesn't have that timing problem. It doesn't need a collapsing star or a slow accumulation of swallowed matter to get started. It only needs enough dark matter in a small enough space, a condition the extremely dense early universe would have satisfied almost immediately. If the model holds up, it doesn't just redefine Sagittarius A star. It offers an explanation for some of the strangest objects Webb has found at the very edge of observable time. Here's what I keep coming back to with this one. We tend to talk about scientific consensus like it's a locked door, reached once, then closed. Sagittarius A star is the clearest example I know of how untrue that actually is. 50 years of increasingly precise measurement, a Nobel Prize, a literal photograph, and underneath all of it, the honest answer is still, we have never actually proven that the darkest object in our own galaxy is a black hole at all. That's not a failure of the scientists involved. If anything, it's the opposite. It's what careful science is supposed to look like. Genzel, Gez, and Penrose didn't claim more than their evidence supported, and the Nobel Committee didn't either. That careful wording in the citation wasn't an oversight. It was honesty, deliberately preserved in the most prestigious sentence in physics. The consensus around Sagittarius A star being a black hole is strong for good reason. It's just not the same thing as proof, and pretending otherwise does a disservice to how science actually earns its conclusions. Slowly, skeptically, one ruled out alternative at a time. And there's something almost humbling in the shape of this particular mystery. The object closest to us, the one we've measured most intensely, tracked with the most instruments, photographed with a telescope the size of the planet, is still the one we can't fully claim to understand. Not because we haven't looked hard enough, because looking hard enough was never going to be sufficient on its own. Some questions don't yield to more data of the same kind. They require a genuinely different kind of evidence. A photon ring nobody has captured yet. A dark matter particle nobody has directly detected yet. Before the door actually closes. It's tempting to treat that as frustrating. A story without a satisfying ending. I'd argue it's the opposite. The willingness to keep the question open, to let a Nobel Prize-winning discovery coexist with a 50-year-old alternative theory, without forcing either one to be declared the final winner before the evidence is actually in, is what separates real science from certainty theater. Sagittarius. A star isn't unresolved because our instruments failed. It's unresolved because the people studying it refused to call it finished before it actually was. So, somewhere at the exact center of our own galaxy, 27,000 light-years from where you're sitting right now, there is an object we have named, photographed, and awarded a Nobel Prize for finding. And we still don't know with certainty what it actually is.